The kinetic theory of gases allows us to relate macroscopic quantities such as pressure and temperature to what the individual gas molecules are doing. So it describes gas behavior due to molecular motion. The assumptions that go into the kinetic theory of gases is, first of all, that the number of molecules is large. We have lots of molecules making up any gas, and the separation is large compared to the molecule size. So if you have a container of gas, most of the container is empty space with the gas molecules flying around inside it. The molecules obey Newton's laws and move randomly. Another assumption is that there are no long-range forces, so molecules only interact when they bump into each other, and they will also collide elastically with the walls of the container that they are in. So basically, they're moving randomly around the container, bumping off of each other and the walls of the container. The kinetic theory of gases also works only for identical molecules. So that means that you can use the kinetic theory of gases when you just have one type of molecule or one type of atom that makes up the gas. And it doesn't work for mixtures of different gases like air. Air is a mixture of nitrogen and oxygen and argon and some other things. And so the kinetic theory of gases wouldn't exactly work there. You'd have to modify it a bit for a gas mixture. So some of the predictions of the kinetic theory of gases is that you can relate both pressure and temperature to the motion of the gas molecules. So you can see in this first expression, pressure is equal to 2/3 the number of gas atoms or molecules divided by the volume of the container times the average kinetic energy of the molecule. So there is a direct relationship between the pressure and the speed with which the atoms are moving around and the kinetic energy that they have. So if they move around faster, they're going to bump into the walls of the container a lot more often with more energy and increase the pressure that the gas has on the walls of its container. Another expression that's very useful is that 1/2 mv squared, so this is once again the average kinetic energy of a single atom or molecule that makes up the gas, is equal to 3/2 times Boltzmann's constant times the temperature. And so this expression encapsulates the idea that temperature is a measure of the average kinetic energy per molecule. So if the energy increases, the temperature increases as well, as the atoms or molecules that make up the gas fly around faster, the temperature will increase.